Jede Folge ein neuer Streifzug durch die Faszination Wissenschaft. Das ist Hessen schafft Wissen, der Podcast mit Erik Lorenz.
Schwarze Löcher üben seit jeher eine große Faszination auf uns Menschen aus. Ein Grund dafür dürfte sein, dass es lange Zeit als unmöglich galt, sie fotografisch abzubilden und dass daher nicht bekannt war, wie sie überhaupt aussehen und ob sie eigentlich tatsächlich so existieren, wie wir sie uns den theoretischen Überlegungen zufolge vorstellen. Im Jahr 2019 gelang dann unserem heutigen Gast, Professor Dr. Luciano Rezzolla, das ist ein italienischer Astrophysiker und Professor an der Goethe University Frankfurt, ihm gelang es mit der Forschungskollaboration des Event Horizon Telescope einen bahnbrechenden Durchbruch zu erzielen. Er gehörte nämlich zu den allerersten, denen es jemals gelang, fotografische Aufnahmen eines supermassiven schwarzen Lochs zu erstellen. Und diese Aufnahmen, vielleicht erinnert ihr euch, die sind damals auch um die Welt gegangen. Rezzollas Forschungsschwerpunkte sind astrophysikalische kompakte Objekte wie schwarze Löcher und Neutronensterne, die sprechen wir nachher auch noch kurz an, die er mit Hilfe von Supercomputern untersucht. Ich muss euch vorwarnen, ihr müsst euch in dieser Folge ein bisschen konzentrieren. Wir haben das Gespräch zudem auch auf Englisch geführt und es geht inhaltlich schon ordentlich zur Sache. Aber wenn ihr aufmerksam zuhört und euch vielleicht ein bisschen anstrengt, dann verspreche ich euch, es lohnt sich, denn die Themen, über die wir sprechen, die sind, ich habe es schon gesagt, die sind wirklich faszinierend. Dazu gehören Fragen wie kann ein schwarzes Loch nun eigentlich fotografisch abgebildet werden? Wie hat das also geklappt 2019? Was bedeuten schwarze Löcher und die Fotos von schwarzen Löchern? Was bedeutet das für die Wissenschaft? Was sind Neutronensterne? Sprechen wir kurz an. Und was geschieht, wenn sie kollidieren? Diese und viele weitere Fragen besprechen wir nun also in dieser Folge von Hessen schafft Wissen und ich wünsche viel Spaß dabei. Bitteschön. Hi, Professor Dr. Rezzolla. Welcome to our show and thank you so much for making the time.
Thank you. Thank you for the invitation.
Today, we are venturing into the universe with you, starting with a phenomenon that will likely capture the immediate attention of many listeners. I hope so anyway. It's a really fascinating topic, at least as far as I'm concerned. I want to talk about black holes. And to many, I'd say that sounds pretty mysterious, unimaginable even, gigantic. Let's start with a very exciting recent discovery I've read about in the news just a couple of days or weeks ago. We are recording this conversation in April 2024. A new black hole was discovered in our Milky Way. Have you heard of that?
I have, but I don't know the details of this black hole. Yeah. I just know that it is a stellar mass black hole. It is a black hole that is produced as a result of the collapse of a massive star. So at the end of the life of a massive star, these stars tend to explode. And what is left at the center of these stars is a very dense object, which can become a black hole in some cases. That's because in astronomy, we know that black holes come mostly in two sizes. Stellar mass black holes, which are of the order of few tenths of the mass of our Sun, and then the very big guys, the supermassive black holes, which are instead normally found at the center of galaxies. Like at the center of our galaxy, there is one, which is called Sagittarius A star. At the center of the M87 galaxy, there is another one, which is called M87 star. And I'm mentioning these because these are two black holes for which we have taken images. So we're pretty certain that something that looks like a black hole is at the center of these galaxies.
Yeah. But the way you're talking about it right now, I feel like this new black hole that has been discovered, I read about it's like 33 times as big as the sun. You wouldn't consider this to be a gigantic black hole. It doesn't seem to be super exciting to you.
No, actually, it's a pretty average black hole, let's say. It's the type of masses that you would expect, the type of black holes that we actually observe with gravitational waves. Black holes of this size are very hard to find.
Yeah.
But we know that there are many, many, many of them, millions, tens of millions in our galaxy only.
Oh, okay.
And because they are so small, they are not easy to find. But once you find them, you realize that, okay, so this is just a member of a family which is very large, and it's good to have nailed it down. But in terms of, breaking something unexpected or bringing something unexpected, I wouldn't say this is the case.
Okay. And when you say it is so small, that's why it's hard to find. I mean, 33 times as big as the sun. To me, that doesn't sound small at all.
Okay, so you see, I was referring to size in terms of length.
Yeah.
While you think in terms of masses. So in terms of masses, you're right. It's a very massive object. It's, much more than the whole solar system. In the solar system, the total mass is essentially the mass of the sun, because us in planets make up a very small contribution. So the mass of the whole solar system is pretty much the mass of the sun, and yet this black hole has a mass which is 30 times that. However, in terms of size, if you were to make a black hole out of our sun, you would get something of the order of 3 kilometers. 3 kilometers only.
Oh, wow.
Okay. So if you have now 33 times that, you have about 100 kilometers. So you have an object that in size, if you were to walk around it, it would be just like a big island. So in that sense, it's not particularly large. And because it's so small, you can imagine being a very large distance is actually a teeny tiny speck on the sky. And that is why it's so difficult to measure with the observations.
Okay, yeah, that puts it into perspective for me. But you have mentioned in passing, just a few minutes ago, another black hole that excited you a little bit more, I believe. And you mentioned that you and your team, you managed to take some images of some black holes. And in fact, in 2019, together with the research team of the Event Horizon Telescope, which you lead or led, and back then you achieved a real major breakthrough in the exploration of black holes, because you generated not an image of a black hole, you, as far as I know, you guys generated the very first image of a black hole ever, and it went around the whole world. It was shown, I believe, by more or less every major news outlet in the world. I have certainly seen it in books, on TV, on websites, and so on and so on. So yeah, the very first image ever. That must have been incredible.
Yeah, it has been incredible for a number of reasons, maybe some which are less mundane than you may think.
Mm-hmm.
First of all, when we started looking at these objects, we knew that there were two objects that we could, in principle, take an image of. Let me explain why.
Mm-hmm.
If you want to take a photo, you know that you need to have a certain resolution, minimum resolution, so that you can see a detail. Below a certain resolution, you will just see a very blurred image. And now we're really hitting the limit of our technology. The highest resolution that we can, with the best instruments we have, we can achieve is 10 micro arc seconds. So it's 10 millionths of a second of arc, or to put it into more practical terms, it's like trying to take a photo of a coin which is sitting on the surface of the moon.
Mm.
So extremely small and extremely hard to measure. So in order to see something that is so small on the sky, you need two things. You either need a very big black hole that is at the right distance, or you need a smaller black hole that is not a very large distance. And the two candidates that we thought matched the profile were exactly these two. M87, which is in a distant galaxies, but is a very big object, and Sagittarius A star, which is instead in our galaxy, is very close to us in terms of distance, is 1,000 times more close, but is also 1,000 times smaller. So when you balance the two things, you end up with two objects which are almost of the right size. But we didn't know that yet. When we started doing all of these observations, we didn't know what exactly was the mass of M87. There was one estimate, there were two estimates, and they differed by a factor 2. The low mass estimate was the right one. It would have been too small for us to actually see. It would have been just a single blur and nothing else. Luckily, it wasn't. That the right estimate of the mass was a large mass, which is 6.5 billion solar masses. And that's why we could see it. So it is striking that we went into this endeavor with a very high chance of a complete failure. And we were lucky enough that, they didn't end up in that way. Another interesting aspect of what you remarked is that it's true. The image was released on April 10th of 2019. On April 11, it was on all the newspapers, the first front page of all newspaper. And it's been calculated that within the first 24 hours, 4.5 billion humans have seen the image. That's the very large majority of the people that are technologically connected. So in particular, if you were in Germany, either you were in a cave or were you completely drunk, not to have seen it in the first 24 hours.
And given that you work in a sphere, in a world of astrophysics, where you deal with a lot of theoretical ideas and complex formulas that are not easily understandable for most people, what did it mean to you that so many people saw the output of the work that you and your team put into this?
That's a very good question. It meant that I could now explain much more directly a concept that otherwise I would explain on a blackboard in terms of an equation. And this may seem, a detail, but actually it is not, because all of a sudden, the concept of a black hole and the possibility of measuring the presence of an event horizon, which is so far been, it's essentially impossible to measure in terms of light radiation. Well, we show that this is in principle a testable object, something you can test. And this is it's a cornerstone in our approach to science, because starting from Galileo, who defined this method first, all of our science is built on the possibility of formulating ideas, theories, and then checking whether or not this theory is correct. And some of the theories are fantastically beautiful. They have all the things you would like to see in a theory, and yet if they don't match reality, they're just wrong. In the case of black holes, this is one of those examples where you can build a lot of interesting and very compelling theories from a mathematical point of view, but maybe they are not the right ones. And this technique that we have employed has opened the possibility of starting to apply the scientific methods to black holes. Because if we have a conversation, let's say at a bar, you and me, and you defend a given type of black hole and I defend another type of black hole, and now our predictions are different, now we can make an experiment and see who is right. Up until 2019, this was not possible. We should just have continued drinking and discussing, but now we have the possibility of settling such an issue. And to me, this is a fundamental contribution to science.
Yeah, it's great, because beforehand, indeed, black holes were a more theoretical concept and idea, and now you have something in your hands that you can look at, that you can observe throughout the years even. I know that you keep photographing the same black hole still all the way till this day to
Indeed.
Also see, are there changes and stuff? So to increase knowledge based on these photos. So what insights can we draw from photos like those? Does it help you and your fellow scientists to really understand more about black holes, or is it not mainly a representation of what you've already calculated mathematically anyway, and now you basically can say, this is what it looks like?
So, okay, there are two levels in the answer to this question. The first one, having this image helps you digest the idea. I'll try to explain what I mean. Black holes have been formulated more than 100 years ago. Actually, it was someone from Frankfurt, Karl Schwarzschild, who has proposed the first solution of black holes. It takes his name, the Schwarzschild black hole solution. For many years, almost 50 years, this solution was ignored because people didn't really understand it. It looked just so strange, so bizarre. The predictions were so crazy that people thought, okay, this is just an artifact, a mathematical toy of this complex theory, that anyway, the theory is not particularly useful. Einstein formulated the theory of general relativity. It was regarded as, something quite irrelevant, because the predictions he was making were so out of the knowledge of physics that people had at that time. They were considered to be, correct, because it was shown it was correct, but for all practical matters, they were useless. In fact, all of the physics that was developed during this year, quantum mechanics, ignored general relativity completely. They didn't need it. And all the experiments we do nowadays in particle physics, they don't need general relativity. They just need special relativity, because gravity is not an important role. So we have now starting to accept this idea of black holes. And in particular, we are starting to accept the idea that some of the difficulties that come with this concept maybe are just inevitable. I'll try to be a bit more clear on this point. Black holes are objects that have two main features. The first one is that they have an event horizon, that is a surface where gravity is so strong that nothing can leave it. So imagine that you have a spaceship, you can go very close to the event horizon. Actually, you can go, if you have a super powerful engine, you can go extremely close to the event horizon. But once you are at the event horizon and you sit there with your spaceship, then you can no longer pull yourself out. Gravity will be so strong that nothing, not even an infinite energy, will allow you to get out. And that's why they are black. They do not emit light. This means that
the gravity is so strong that even light is being sucked in.
Exactly. Well, more than sucked in, light cannot go out. Light tries to go out, but actually doesn't manage. It's about like swimming against the tide. If the tide is very strong, no matter how strong of a swimmer you are, you will not be able to go against the tide. This means that there is a region inside the black hole which is completely inaccessible to you. We know exactly what happens inside a black hole. We know that the laws of physics, how they behave, but you can't test it. So I've written a book. In this book, I come up with an analogy about how frustrating this is. And it's a dialogue between two chaps that are outside the black hole. They are on a spaceship and just looking at it. And they're having a conversation. One of them says to the other, "Oh, I know exactly what's inside a black hole." And the other one says, "Sure, I also know. It's written in the Einstein's equation." And the first one says, No. What's inside a black hole is actually a fantastic ice cream shop. They have all the flavors you can imagine. And in particular, they have the best ice cream of my flavor. The second chap says, "Obviously you're wrong. You can't produce an ice cream shop inside a black hole. It would be destroyed by a very strong gravitational force." And the first chap says, "Well, maybe so, but you can't prove me wrong. And so I will insist it's an ice cream shop." So having this impossibility of going inside a black hole, making an experiment and tell the one who is outside, "Look, there is no ice cream shop," is very frustrating for science and physicists in particular, who want to be able to test everything everywhere in the universe. So all of a sudden, a black hole creates a door beyond which you cannot go, or if you go, then anyway, you cannot tell anyone whatever you find. So this loss of information is frustrating. Another important property of black holes is that at the very center, all the laws of physics break. At least in the classical theory of gravity as devised by general relativity. We think that's wrong, we think that's a limit of the theory. We think that once you get very close to the center, quantum mechanical effects need to be taken into account, and they are not in the Einstein theory. And so something else, which is not a singularity, that's this place where everything becomes incredibly and infinitely strong, has to be replaced with something which is still very strong, still extremely intense, but not infinite. So there are these two things that black holes have that physicists have very hard time accepting. And so for me, making this image was first a way of saying, okay, maybe I should really accept that black holes exist. That's me.
Yeah.
At the same time, that image has also triggered a lot of colleagues of mine in saying, actually, you know what? My black hole is, if I change my solution in this way and that way, actually can fit the observation. So maybe what you have taken a photo of is not a black hole as Einstein predicted, but is a black hole as I predict.
Okay, so your story with the ice cream shop, basically, that's what's unfolding, despite the photo.
But you see, the point is, in this case, it's just a matter of time. As our observations will improve, we will be able to tell the difference from whatever theory you are suggesting. Right? In the other case, that was intrinsically impossible. There is no way in which you can break this paradox. And so there are other colleagues of mine who are actually saying, no, you know what? What you're seeing is not a black hole at all. It is something that looks like a black hole, but it's not a black hole in that it doesn't have an event horizon. It's a very compact star, so compact that its surface is almost close to the event horizon, but it's not right at the event horizon. It's a bit larger. Mm-hmm. And so from your observations, you cannot tell them apart. So you can see, theoretical physicists can always find new ways out of to promote their own ideas, and this is the nature of the game. It's a cultural, intellectual game in which you try to find a way of proving, of disproving someone else's idea. Of course, the idea of the star is plausible, is mathematically correct, but it's very hard to produce. So if you are a down-to-earth scientist, you would ask yourself, okay, but how do I produce such an object? We know how to produce black holes, but producing this very sophisticated and exotic solution is much, much harder. So the debate is still on, but let's say there is a large majority of the community that thinks these are black holes as predicted by general relativity. And then there is a very active and loud and energetic part of the community who is trying to prove them wrongly. So it's interesting.
It's super interesting. I have a few follow-up thoughts and questions on that. First of all, of course, it's super fascinating to me to imagine that Einstein, with his theories decades and decades ago, came up, and then, of course, predecessors, you mentioned some of them, that had the first thought of something like a black hole might be in existence. But decades and decades after these thoughts originally evolved to now have something that could be a proof that all these theories are actually potentially true. So that's super exciting. I want to mention the story that you told, the ice cream analogy. You mentioned it's from a book that you wrote. I believe that book is called Die unwiderstehliche Anziehung der Schwerkraft. Is that correct?
That's correct, yes. Yep.
Okay, perfect. Just as a little reference for our German-speaking listeners, if you want to learn more about astrophysics and maybe want to understand even more than you do in this one conversation that we're having right now, this book is highly recommended. Die unwiderstehliche Anziehung der Schwerkraft. And finally, before coming back to the photo, to the image one more time, I'm wondering, when I listen to you talk about these theories and these different astrophysicists with their different ideas, and I mean, you turn it into an extreme example with the ice cream theory, but is it sometimes a little bit frustrating for you as well that most of your work remains in the realm of theory, and that, as opposed to, for example, a biologist who can travel on site, and if it's not a molecular biologist or whatever, he can observe things, he can touch things, he can count things. But you have to, I mean, either you go into space one day yourself. I don't know if that's an intriguing thought for you, but otherwise you have to rely mainly on theory.
Well, first of all, yes, it's one of my dreams to go into space. I don't know if I will ever manage to that, because it's, as I mentioned again in the book, the gravity has such an attraction on us. And when I say attraction, I don't mean just in terms of physical interaction. I really mean in terms of the appeal it has on our minds. That's because it's an interaction. It's the only physical interaction in which we are conscious. All the other interactions that, regulate our bodies, we are not aware. The forces that keep our molecules together, we have no sense of this.
We take them for granted, and we cannot even imagine a world where they don't exist. It's just a given.
Not only that, while you can feel yourself sitting and you know how much it takes for you to lift an arm because you're making a work against gravity, you have no idea, or that some of your atoms are being split or some are combining, because it's something so small that is beyond your capacity of perceiving it, while gravity is on the right scale for us to experience it. In fact, we experience it all the time, and even before we are born. Again, this is something I discuss in my book, where I say that our experience with gravity starts even before we are born, and there are ways in which this can be proven in terms of an experiment which is carried out on little children. But going back to your question, yes, it is frustrating. It is frustrating, especially when you are debating with people who are not flexible enough to accept that there is reasonable evidence, compelling evidence. It's not a proof, but if you use Occam's razor argument, then this is the most reasonable and natural explanation and doesn't require a very complex and possibly artificial explanation. When I am so frustrated, I come up with a consoling thought, and that is, I want my students to be equally excited about science. And so the students, they will train, and so the students of the students of the students. And this can only be possible if there are still open questions. If during my lifetime, all of the open questions about gravity were resolved, I wouldn't find a single student wanting to do research in gravity, because all of the interesting things have been addressed and there isn't much to do. And so I think in a way it's good that there is so much debate, that there are so many ideas, there are many pro and against the idea of black holes, because this gives people who are interested in these topics the opportunity to study them better, to find new arguments, to find new evidence, to find other ways in which the other side, or those who are not believing into black holes, can be confronted with.
Yeah. Helps you guys to stay hungry. And in another interview, you also said, I quote you, if you know what you're doing, you're not doing research.
Yeah, exactly.
So that's also a good argument. There needs to be some open questions left for science to make sense and to remain exciting, of course. But I would like to come back to that image one last time. We covered it pretty well, but I want to get back to how you describe that it is extremely difficult to generate an image like that for a multitude of reasons. You mentioned that the massive gravity attracts all the light or prevents it from ever coming out of the black hole. So that's why it's black. That's why it's super hard to see. Also, it's pretty small because it's so compact, I guess is the right word. So anyway, there's a lot of reasons why it's super hard to photograph them. It's why it hasn't been done until very recently by your team and you. So I wonder, could you elaborate what we actually do see on that very famous image?
Before I answer this question, let me explain why it is difficult to make that image technologically, independently of whether it was a black hole. So imagine that we take M87 as roughly the size of our solar system. So imagine you want to take
the big black hole that you photographed.
Yes, yeah. M87 size is the first black hole, is the large black hole in the galaxy M87. And it has the size, so that image has the size of the solar system. So imagine the outermost planet in our solar system, Pluto. Imagine filling all of that area with a light, and to put it at 65 million light years away, it would be just a teeny tiny dot.
Yeah.
So if you want to now see this teeny tiny dot of light, you would need a telescope, a very large telescope, because the bigger the telescopes, the higher the resolution, the ability to see teeny tiny things. And
that's what you talked about when you mentioned it's like photographing a coin lying on the surface of the moon.
Exactly. So you need a telescope. You calculate how big this telescope has to be, and you find a disappointing answer. The telescope has to be as big as the whole planet. So either you say, give up because I don't have a telescope as big as the whole planet, or you say, maybe I can come up with a virtual telescope which is as big as the whole planet. And so people have solved this problem already in the 70s and have developed a technique which is called Very Long Baseline Interferometry, or VLBI, that does exactly this. Essentially, by putting together two telescopes which are at very large distance between them, you can imagine you are building two tiny parts of a large telescope as large as the separation between these two points. This is called interferometry, this technique, and allows you in this way to make images of objects as tiny as the one we have done. So from a technological point of view, we had to be able to use this technique to reach the highest ever resolution used in human history. So we use a number of telescopes. In particular, we used 8. And these are all located in different positions on the planet, from France to Spain to the South Pole, and then over to the United States, and then even to Hawaii. And we create a network of telescopes in this way. And as the Earth rotates, there are always at least 2, if not more, telescopes which are observing the object and therefore are collecting light. So technologically, this was the main difficulty in making this observation. Then, of course, there is the difficulty of making this in terms of a collective effort. Scientists like to work together, but not all the time and not everybody. And so having these collective efforts are require a lot of preparation and a lot of logistical work that needs to be done. That was another challenging aspect of this observation. But I think your question was something else. Can you remind me what was it?
That's no problem. First of all, I just want to intersect in terms of just the technological collaboration that you facilitated with all these telescopes around the world and so on. To me is is mind-boggling. I mean, I'm already happy if I manage to put the right cables into the right microphones to record interviews like this. So it's amazing. It's amazing what you're doing. But anyway, the question was, given that it's super hard to photograph them because they're far away, we need massive telescopes, bigger than they actually exist, except for if you have creative ideas like the one you just described to work with the technology we have. But also a black hole is just a black hole. It's basically a nothingness. So that's why I want you to explain for people maybe who haven't even seen the photo. What do we see on it? What does it look like? And what is that thing that we see?
Okay.
Because I don't think we see the actual black hole itself, right?
First of all, we cannot see an event horizon. But the event horizon is just a piece of the picture.
Yeah.
It's just a part of a black hole. A black hole is made of an event horizon, but also all the surrounding around him has very specific properties. What we see, let me simplify the picture to the extreme. What we see is a donut, and this donut is not symmetric, okay? So imagine that we see a ring of light, a thick ring of light, and there is one part, the top part, which is less bright than the bottom part. And I'll try to explain now why it looks like so. What we see is matter, a plasma in particular, that is going around the black hole and is about to fall onto the black hole. This plasma, because it's very dense and is moving at very high speed, is producing light. So what we're seeing is the light produced by the plasma that is about to fall onto the black hole. That is why it has this circular shape, because it is essentially matter that moves around on circular orbits in a disk. So there is an accretion disk, we say it. There is a disk of matter that is falling, and this is roughly a circle. Now, the reason why it is not a uniform circle, it's not a uniform donut, but is a donut which has fluctuations, is because the density in this disk is not uniform. And in particular, there is one part of the disk that is coming towards us. There is a slight inclination. And if you think about a disk oriented with respect to you, there's always going to be one portion which is closer and one portion that is further away. The portion that is closer is moving towards you. And so the light that is emitted by this portion is more intense than the light that is moving away from you. This is called a Doppler effect. It's not very different from the Doppler effect we experience when we hear a siren of an ambulance, and is amplified very strongly in when you move close to the speed of light. So the reason why we see half a donut is because there is matter that is going around a black hole and is about to fall, and it's on a disk, and this disk has a certain inclination such that there is a part which is brighter than the other.
Okay, thank you. That makes sense. I'm not sure how to ask that question, the next one that I have in mind, without opening a huge can of worms, because I'm sure you could talk about it for hours. But maybe there's a way to summarize it, because early on in our conversation, you have mentioned Einstein a few times and his theory of relativity. And I know that you engaged with that theory a lot scientifically. You appreciate that theory as beautiful. I mean, it is one of the most famous theories ever thought of. How does your work and this image and what we see and what it shows us, how does that relate to Einstein? And how does that suggest that his theory, in fact, is probably correct, at least with regard to the black holes?
So there is a theory which is well known. You can calculate what are the predictions of this theory. You can predict what a black hole like the one we think is there would look like. And you realize that such a black hole is matching extremely well the observation. So there is a good match between theory, the prediction of theory, and the observations from astronomy. So you would say that's good enough for me. That is exactly what I predicted. That's what the theory predicts. So I think this is a verification of the theory. But my work with general relativity is not just restricted to taking images of black holes. I spend a lot of time making another important prediction of this theory, which are gravitational waves. Gravitational waves is something that is really a new window that we have on the universe. It's a different way of looking at the universe itself. And you certainly have seen fireworks.
Mm-hmm.
Now, imagine that you see fireworks where you don't hear the sound. You just see the light, the beautiful light, all the colors, but you don't hear the sounds. That's essentially what has happened with astronomy up to now. We saw the light. We didn't hear the sound. We didn't hear anything else that accompanies that light. But we know that together with that light, actually, there is a lot of other signals that are produced and reach us. And so by opening these detectors, by turning on these detectors, it is as if we put the sound on this fantastic show that are fireworks. And we can see that show in all of its beauty. In the case of fireworks, what we receive in addition to light are sound waves, in particular the shock waves produced by the explosion that takes place in the chemical reactions. In the case of gravitational waves, we don't hear sound waves, but we hear something, we measure something that is a wave, just like the sound waves, and is a transverse wave that reaches us and is produced by the same source. So it is another way in which I use this theory of general relativity, and I study how two black holes of two neutron stars produce gravitational waves when they are about to merge and collide. And that's a fantastic exercise, and it's a fantastic laboratory to study physics and gravity.
Gravitational waves, that is another truly fascinating topic. You are working, as you mentioned, on this topic intensely, and you have done so for a while now. You and a few other researchers had predicted such gravitational waves in pretty elaborate theoretical calculations based on Einstein's theory, and you started to predict all of this as early as 2010, I believe. And then in 2017, gravitational waves, indeed, from two colliding neutron stars, this is also something that you just mentioned, they were indeed detected for the very first time. So that also means that all of these theoretical models, in this case, were confirmed.
Indeed.
I'm sure there are also some scientists maybe that have other ideas about what happened, whatever, but I mean, that must have been super exciting for you.
It has been super exciting, indeed. I feel myself extremely lucky as I have experimented within a matter of 5 years, two major confirmations to a lot of the work done by me, my group, but also my colleagues in this topic. And it was great to see that all of these calculations were not only right, and they actually helped detectors to see the signal, because detectors have an extremely small chance of getting the signal because they are always working in what is called signal-to-noise ratio of order 1. Now, the reason why you're listening and hearing my voice is because my voice is much louder than any other noise that unfortunately is present, but is maybe a factor 1,000 larger than the noise, so you can hear my voice and you can understand what I'm saying. These detectors work with signal-to-noise ratio of order 110. That means that the signal is only 10 times larger than the noise. It's comparable with the noise. So the only way in which you can hope to see and measure something is if you know in advance what is the signal. It is as if in this conversation you can hear some of the words I'm saying, and out of these words you can build up whatever you cannot because of the noise. And these techniques, therefore, need the knowledge, the prior knowledge of what is the signal. And that's what our calculations provide. And it was exciting also because there were some ideas that were confirmed by these observations. In particular, there was the most important one is in astrophysics, there are phenomena which are called gamma ray bursts.
Mm-hmm.
These are flashes of light in the gamma rays that we see essentially once a day, and they are extremely powerful. So imagine that in the sky, somewhere in the sky, every day you see a flash of light, and this flash of light is telling you about something that has happened in the most remote corner of the universe. And the only reason why you see it is because it's so bright that you cannot miss it. What produces these things? It's been a puzzle for many, many years. There's been a conjecture that, you actually are almost forced to do, that given all the properties of these flashes, they must be related to the collision of two neutron stars.
Yeah.
We know that neutron stars exist in binary systems. We know that the two neutron stars are getting closer and closer to them. But there was never the possibility of measuring both the collision and the emergence of a gamma ray burst. And instead, in 2017, that's exactly what we saw. We saw the gravitational wave signal up until the two stars collided, not quite at the end, but almost at the end, and then nothing else. The signal in gravitational waves disappeared because it became too weak for the detectors to be seen. But then 1.7 seconds later, we saw light. There were satellites and all of a sudden got exactly from that direction a flash of light. And that was fantastic.
And that is this fast radio burst that you mentioned.
No, that's the gamma ray burst.
Oh.
That's a gamma ray burst. So it's a gamma, it's not radio.
Yeah.
And this has been the solution of a puzzle that was been long standing for many years about whether or not gamma ray bursts, particularly this type of gamma ray burst, short gamma ray bursts, were produced by the collision of two neutron stars. So I feel myself extremely lucky that I've lived in these years.
And especially I've read that a research proposal from you previously was rejected for a neutron star research, as the reviewers considered it a pretty unlikely that we would be able to measure these gravitational waves from colliding neutral stars at any time in the near future.
Yeah, this is a very sad story. It's a very sad, because I spent a lot of time submitting.
I didn't want to make you sad. I felt it's like a pretty happy end story.
Well, no, it is sad because, the proposed research was not funded and so could not be pursued for reasons which were then shown to be wrong, because we had applied for research funding to do research to study exactly this process, and the reviewer said this is a fantastic idea. The scientists are excellent, but we just think that this is not going to be happening so often, so then this funding should not be used. And then just a week later, GW170817, this binary neutron star merger, was announced. But that's life in science. For one successful proposal, you have to write many that are actually not funded.
Yeah. Indeed. That's the challenges and the successes that you can have by following a scientific career. And I want to just mention for our listeners, of course, we have now not fully explained your work in neutron stars and their collisions and cosmic catastrophes. This would be a whole nother conversation. We cannot do justice to these topics, but it was exciting to hear you at least touch upon them to get a better understanding of what you deal with in your scientific work. And for the final part of our conversation, because we do have to come to an end, I don't want to take too much of your time, I would like to briefly look back towards the beginning of all of this for you. How and when and why did you personally become interested in all of these questions and in astrophysics overall? How did it start for you, this passion?
Okay, that's a tough one.
Oh, I thought that would be the easy one.
So I think when I was a student in my high school, I had a number of interests, and these were very diverse. I was interested in medicine. I was interested in marine biology. I was interested in astrophysics. And then essentially it was an exclusion game. I realized that I was not interested in the type of work a medical doctor would be doing. I was able to cope with blood and traumas and so on. Actually, I was a volunteer of the Red Cross and serving on ambulances. So trauma was not a problem, or blood was not a problem. I couldn't cope with the fact that with people suffering. I thought it was, too impactful on me. And so I looked into the other two alternatives. Marine biology was the one that was, taught in my university, was mostly to do with shells or very small animals living on rocks, which wasn't really exciting to me. And so what was left was astrophysics, which was another passion for which I had studied a lot. So these three things I had studied independently on my own. And then I realized that there was no counter-indication for astrophysics, and that's exactly what I then continued to study in my universities.
No strong reason against it.
No, exactly.
And was it pretty clear pretty early on for you that you would go into research?
So I definitely like the idea of doing research during my time at the university, and I enjoyed doing it also later on. But at one point, I actually thought of leaving science for doing something else. And I do believe that while science is a very exciting area and a good way of spending one's life, it's not the exclusive way of spending one's life. And there are many interesting things that one can do outside, and someone with a creative mind can find many different ways in which his creative mind can be applied in other contexts. So I think I made a choice. I'm happy about a choice. I think it's a good way of using my skills and my interests, my passion. But there are many other things I'm very passionate about, and I hope to dedicate more time in the future to them.
And when you look at your graduates, what would be some examples for what they are doing that is not scientific work and research after graduating?
So some of my students are doing a lot of money in finance. And
is that one of your interests that you want to pursue later on as well?
No. But I think it's interesting that you train students to study black holes and then they end up producing black holes in financial markets.
That is dark humor, but I like it. Yes.
Yeah. Others are working as software developers, and I don't have anyone who has done a more, philosophical switch of life. But I think they're all doing very interesting things, and some have become politicians out of all things. So I think some are working in very secretive departments of the German government. Mm-hmm. So it's interesting how someone who is trained in theoretical physics can actually be recycled in many different forms, because essentially what you teach a student in theoretical physics is how to solve a problem, a complex problem, how to dissect a complex problem into parts that you can handle either mathematically or with computers. And so I'm pretty happy about this diversity, if you want.
That means if listeners, maybe there's one or two younger listeners who are thinking about what to study, if they're considering something like theoretical physics, then probably that would be something that they should be passionate about, which is trying to solve really, really, really complex problems.
Yeah.
Is there anything else that you would say that would be something that you would look for in your graduates? That would be a good idea to have as a skill or as an interest?
Well, passion, I think in science, but also in life in general, the skills are important, but skills can be developed up to a certain level. Okay. Mm-hmm. I don't know how to play an instrument, but I think that if I were to dedicate myself to playing an instrument, I could play an instrument to a certain level. I wouldn't be a virtuoso probably, but I would be able to play something. So developing a skill, whether it is, a manual skill, a musical skill, or a mathematical skill, this is something that can be done, and you can teach and you can train people to learn these skills. On the other hand, learning what is your passion is fundamental, because if you then can work in the direction of your passion, then you have a fantastic power. You have the skills and the passion, and you can really, enjoy what you're doing and not feel the weight of spending many hours and seeing many rejections of your proposals and so on, because you're driven by passion.
Yeah, gives you the superpower to push through these obstacles. That's good advice. Yeah. To finish up this conversation, we have a category in each of our episodes where I start a sentence and would invite you to complete it if there's something that you can think of. Let's just give it a try. It should be pretty painless and harmless, I hope. I am passionate about astrophysics to this day because
many of the things I predict are correct.
And it feels good to be right.
And it feels good to be right, yes. Absolutely.
That makes sense. A role model in astrophysics or in science overall is?
So I like very much Kip Thorne.
Why? Who's that?
Well, Kip Thorne is an American physicist, Nobel Prize laureate. And as, someone that I have interacted with when I was younger. And he's a person that has shown to have a very multidimensional personality. So not only is he an excellent scientist, He's also interested in many other aspects of life. In particular, one aspect that you would think would not be relevant for scientists like Hollywood movies. Mm-hmm. He's been involved in curating some Hollywood movies. The most celebrated one is Interstellar, where he provided scientific consultancy.
Oh, wow. The movie by Christopher Nolan.
That's right. Mm-hmm. And so all of the images there are almost right. And that's because he was, and all of the physical analogies are right because he was making sure that the physics was correct. Not everything. I mean, this is Hollywood.
Yes.
But science is much closer to reality than it is in most science fiction. It breaks a bit the idea of a scientist as someone that is, monochromatic, just thinking about black holes and mathematics, but also is, a much more open and diverse mind. Mm-hmm. That's a good role model for me.
Makes sense.
I try to be that. I try to have other interests. I try to have other passions.
I often advise my students to...
Oh, that was a sentence. Sorry. I often advise my students to take a break.
And I believe you really deserve a break too, really soon. That's why let's try one more and then we're done. In the future, I see the most exciting research or areas of activity in astrophysics in
measuring the post-merger of a binary collision. Now, that requires some explanation. So neutron stars, they spiral around each other faster and faster and faster, producing gravitational waves, which are at a higher and higher frequency. It's like a signal that is increasing in frequency, like a beep. Now, this signal then ends up with a very high frequency tone. And this is produced by the object that is the result of the collision. So when the two stars collide, they normally don't produce a black hole. They produce another object, which is called an hypermassive neutron star. It's an object that is unstable, is there for about a second before collapsing to a black hole. And what this object is made of and how it keeps itself alive and what it does is dependent very much on what is the composition, the internal structure of neutron stars. So neutron stars, we haven't discussed them at all, but they are beautiful objects, almost as big as Frankfurt, but with a mass of the order of the solar mass, actually a bit more. So they are extremely fascinating objects, but we don't know what they're made of inside because the matter there is in conditions so extreme, we can't really produce them on Earth. But if we are able to measure the gravitational wave signal after this increasing chirping signal, then we would have a way of measuring this. I think in the next decade or so, when we have the ability to measure this signal, that will be the most exciting result that will come out.
Wow. I am rooting for you. I'm keeping my fingers crossed that you will be right once again.
Thank you.
And I'm glad to hear that you won't run out of ideas and more open questions anytime soon. Thank you so much for this conversation. Thank you.
Thank you.
Bye-bye.
Hessen schafft Wissen, der Podcast.